Okay, thanks for coming out once again. So before I start, I sent this email out to all of you this afternoon, but just in case you didn't get it, you can check it out on the Detail website, or you can check your email later. You'll probably get it later, but I'm going to go through exactly what to expect on the midterm, what you should cover, what you shouldn't cover, just for self-containment. All right. So the midterm will take place next Monday, June 13th. It'll span from 2 hours, from 6:10 to 8:10. All right, so it should take you about 2 hours to do it. And you're going to write it here in class, ENG 105, all right? So unfortunately, because of a professionally related matter, this was already booked months ago. I will not be here for your midterm, unfortunately, but your TAs will be here to invigilate. So if you have any questions about the midterm, then you can certainly talk to them. They're very knowledgeable on the topic as much as I am, so you should be good, okay? And then I'll try to have your midterms marked by the next Monday, because they're going to take turns taking part in marking a couple of questions, and then I'll take part in marking the rest. I'll give them time to mark, and then hopefully I'll get it done by the Monday. So you'll see your marks up on the Monday. All right. So you're allowed, obviously, a scientific calculator. It can't be like a graphing calculator, like a TI-83, or something that has very large text-based capabilities. You can't. Just a standard scientific calculator, like a Casio or Sharp or something related to that is perfectly fine, all right? In terms of formulas, you don't have to memorize any formulas. Those formula sheets will be provided for you. Okay, so common for you, transform pairs, properties, trigonometric identities that you may want to use, Euler's formula as well, will be on these formula sheets. And note that I'll be providing formula sheets in both F and omega. So whatever you're most comfortable with in answering, then you can certainly go ahead and do that. Okay. I posted a sample copy of what the midterm formula sheets will look like on our website. So if you go to the D2L website, and if you go to the exam section, at the very top you'll see a section that says formula sheets, and then you can click on that PDF. You can see what formula sheet you'll be expecting on the midterm. Okay, so this will be attached to the back of the exam. You can detach it from the exam, and you can use that as scrap paper, or you can use that as a reference, but you don't need to hand those sheets back in when you're done. You can use those and detach them from the exam, and you can use those as reference as you do the questions. Okay? In terms of answering questions, as I talked about, you can answer them in whichever domain you want to use. If you're comfortable in omega, then go ahead and do it in omega. If you're comfortable in F, you can go ahead and do it in F. All right? I've written the solutions for the TAs to mark such that you can do them in both, and there are marking schemes for both. So answer in whichever domain you're most comfortable with. Okay? So the format of the midterm is very simple. It's just going to be 4 questions. Most of it will be full answer. There may be some discussion questions like, explain why this is happening in 1 or 2 sentences. It's not meant to be a full essay type thing. It's mostly going to be calculation based. There's 4 questions, all right? And below is a rough guideline of how many minutes you should spend per question, roughly. I've timed it out roughly. And this also includes double checking your work. Okay, so the first question is going to take a little long. It just tests to see whether you know the theory behind all the topics that we covered in class. It does include calculations, and then as you start going towards the end, the difficulty decreases less and less. So it gives you kind of a reward when you get to the end of the exam. All right, so 45 minutes for the first question, 35 for the second, and then 20 minutes for the other 2. And this does include, as I talked about, double checking your work. Okay. In terms of what's responsible for the lecture material, you're only responsible for the first 4 lectures, okay? So that's all the material you're responsible for knowing for the actual midterm. So going from the first lecture, it's just a brief introduction, and I'll talk about communication systems, what they're about. And then we get on to a signals and systems review, and then amplitude modulation. All the techniques that we've talked about. So double sideband sparse carrier, AM, single sideband, and vestigial. Anything after this point you are not responsible for. Do not study those. Don't waste your time. Those will be covered for the final exam. Okay, so anything with phase lock loops or RF receivers that we talked about previously, that is for the final exam. Don't worry about those topics. Okay, so just up to and including lecture 4, which is ending with vestigial sideband. Okay, that's all you're responsible for. Don't study anything else other than those 4 lectures. Okay? In terms of tutorial material, I don't believe it's necessary to have a midterm review, because I'd just be covering these questions all over again. The final exam, for sure, I will do a review since we will have time. But in terms of tutorial questions, if you can comfortably answer the first 5 tutorial sets of questions comfortably, if you can do those off the back of your head, then you should be in perfect shape for this midterm. Okay, so you're responsible for the first 4 tutorials. So there's signal systems review, and then there is AM and double sideband sparse carrier. There's more AM, and then we'll talk about single sideband and vestigial sideband, which we'll cover today. So all the tutorial questions up until and including today is all fair game for the midterm. Okay. If you have more time, go ahead and take a look at some questions from the previous years. There's an exam archive with full solutions for most of the midterms and exams. If you can, again, do those comfortably, they're actually much more harder than what we've seen in the tutorials here. If you can actually do those questions even better, you should be in good shape for the midterm. Okay? And that should be it. So any questions regarding what's going to be covered for the midterm? Or are we okay? Yeah. So I made it very clear. How much time you should spend for question, what lecture material you're responsible for, tutorial questions, and all that. So I'm pretty sure I put all the information here. If not, then you can come see me after class. But I think I've covered all the bases here for what you're responsible for the midterm. Okay. All right. So let's get on to frequency modulation. So we've actually finished amplitude modulation on Monday. So we finished with RF receivers. So it was a nice way to end the topic. So we're going to get on to frequency modulation now, which is the next most common way to transmit signals over channels. All right. So here's a brief overview of what we're going to cover. We're obviously not going to cover all these topics today. We're going to spread them out over the next few lectures or so, and then we'll get into the last part of the course. But we're going to talk about frequency modulation, obviously. So we're mostly going to concentrate on these topics today. So this will be today. So taking a look at phase modulated signals and frequency modulated signals. FM is the one that's used the most, okay? And then we'll take a look at bandwidth of frequency modulated signals. Dealing with bandwidth for FM signals is a completely different ballgame. It's actually a lot more difficult to analyze the bandwidth requirements, and we're going to talk about that today, okay? Generating FM signals and stereo broadcasting, that'll be for later. That'll be the second part of AM, which is not going to be covered today, but we're mostly going to cover taking a look at PM, phase modulated, frequency modulated signals, and the bandwidth requirements today. Okay? Okay. So just a quick review of modulation. We've already seen this before, right? Modulation is concerned with varying either the amplitude or varying either the frequency of your carrier wave. Okay, so amplitude modulation is concerned with changing the height of your carrier. The height of your carrier depending on the height and the actual message contents themselves. Okay, so you usually have some sort of message signal. This is what's known as a bass pass or a band pass signal, right? Actually, no, a baseband. Sorry, this should be a baseband signal. So you have some message signal that you want to transmit. You have a carrier signal that is used. That's also narrowband. The carrier frequency is much larger than the bandwidth requirements of your input signal, and then the output is your modulated signal, which is bandpass. Okay, so this is what we've seen before. So in AM, you vary the height of the actual carrier. Okay, so we've seen that already. Okay, so what we talked about, this is before. So this is actually varying the height of your carrier, which is the cosine wave. So this is amplitude modulation, right? This here is what we're going to concentrate on today, where we leave the height of the carrier constant, and what you're doing is you are changing the frequency content. You're adjusting the frequency as time progresses based on the contents of your message. And we're going to talk about that one today. So this is today. Okay? So there's a potential, there's a time varying phase where the phase varies over time, and also the frequency will change over time too. So this function represents a rotating phasor where there's a potential time varying amplitude. In this case, we don't worry about this anymore. This will stay constant. Okay? But we're going to take a look at these two today. So there's a phase that changes over time as well as frequency that changes over time. So this is a definition that we're going to use throughout this course. Okay, this is what is known as the instantaneous frequency. So what the instantaneous frequency means is that it is the frequency that you see at that signal at that point in time. Okay, so when you're taking a look at derivatives, for example, when you take a look at the instantaneous rate of change, it's the slope at that particular point. You can think of this in terms of what the actual frequency is observed at any point in time, at a very, very small point in time. Okay, so this is simply just the derivative of the phase. And the reason why they divide by 2 pi is because originally this here is in radians per second, right? So this actually should be not omega c, but omega I is equal to the derivative of the phasor, of the phase term. And they divide by 2 pi because you want to change it in terms of frequency instead. So we certainly know that omega is equal to 2 pi f, and then f is equal to, let's see here, 1 over 2 pi omega, and that's where the constant of 1 over 2 pi comes from. Because originally it should be an omega. You just take the derivative of the phasor, you get it in terms of radians per second, but you divide by 2 pi because you want to get it in terms of frequency. But it doesn't matter which representation you use, whatever one you're most comfortable with. But in this course, we're going to take a look at instantaneous frequency, the actual frequency in hertz, because it makes a little more sense when you plot out the actual wave over time. Okay, so angle modulation, all right? So you're either going to take the phase or the frequency, and you're going to adjust the way the carrier propagates over time by the message signal. Okay, so you're going to change the phase or the frequency depending on what the contents of the message are, and notice that the amplitude of the carrier remains constant. So remember, in amplitude modulation, you're changing the height of the carrier depending on what the contents of your message are. In angle modulation and also frequency modulation, the carrier height stays constant, but the frequencies, the actual instantaneous frequencies or the frequencies at each point in time change depending on what your message signal contains. Okay, so as I said before, your carrier wave is constant, and then your phase for the carrier is dependent on some function of the message signal. So we'll talk about what functions there are in a minute. But the point is that the information contained in your message signal is embedded in a time-varying phase. So that's very important. So that means that over time, the phase or the frequency of the actual carrier wave may change, and that's dependent on the message signal that you're trying to transmit. All right? Okay, so the first technique we're going to take a look at is what's known as phase modulation. So this is actually very simple, okay? So the carrier amplitude stays constant, so A of t is your carrier amplitude, so carrier amplitude stays constant. We don't change this. The phase will change here. So what's happening here is that your carrier will not only be based off of a carrier frequency, so this is your carrier frequency, but deviations from the carrier frequency that are exhibited by the contents of your message signal will be transmitted, and that is what is being done. Okay, so your message signal is here, so this is your message signal. In this constant k sub p, it's what is known as the phase sensitivity. So what this sensitivity does is that it controls how much of the phase varies over time. So the larger this constant is, this means that very small changes in your message signal will affect the phase very largely. And smaller values of this will mean that very small changes of the message will not actually affect it. So this number will actually make the phase be very large over time or very small, depending on the contents of your message. Okay, so this is what is known as the phase sensitivity. So this, and then this is proportional to your message, and then there's also some initial phase offset. We usually set this to 0 to make things easy, but it can be non-zero at certain points in time. Okay, so the phase modulated signal looks like this. So remember, this is your carrier frequency, and then changes in the carrier frequency are dependent on the contents of your message. So for example, if your message signal was completely full of zeros, then you just have a carrier wave that oscillates over time that doesn't change. And then as soon as you change the contents of your message, if the message goes higher and higher, then the phase will shift towards the right. And then if your message signal goes lower and lower, if it goes negative, then the phase will shift towards the left. So depending on the sign and the and I guess the dynamic range of your message, it'll affect the phase accordingly. Okay, but the general message I want to convey is that the information that's contained in your message is embedded in the phase. So this is actually very important. So the phase is directly proportional to the message. That makes sense. So as the message changes, the phase will also change as well. Okay. Oops, let me go back here. All right. So the next one, which is actually more common, is frequency modulation. This is the one we actually use the most, so this is more often used. Okay. All right. Before I continue, all right. So how this relationship is derived, so remember that this is our phase, all right? And then the instantaneous frequency, this is equal to d by dt of, so this is 1 over 2 pi d by dt of theta t, okay? So you find this by taking the derivative of this guy, okay? In this case, you get 1 over 2 pi, and then the derivative of this is 2 pi fc, and then plus kp, and then m prime of t, and then derivative of this constant goes to 0, right? So that's what we get. And then the 2 pi's cancel, and then this is the relationship that you get over here. Okay, so d by dt is just m prime. So you take the derivative, divide by 2 pi, and then this is the relationship that you get. Okay, so that would be the instantaneous frequency over time. Okay, so for frequency modulation, it's a little different, okay? So what's going on here is that the message signal directly affects the frequency of your signal. So instead of the phase, where you're doing phase shifts, that are delaying or advancing, you are actually changing the frequencies of your signal. So as the message becomes larger and larger, the frequency of your carrier increases. And if the message signal becomes negative, then the frequency will decrease, okay? So that relationship is done through this guy here. So the frequency, the instantaneous, or the frequency at each point in time is directly related to the message signal itself. And if you want to go to this point, it's actually very easy. All you have to do is, well, remember that the instantaneous frequency is equal to 1 over 2 pi, and then I'll call this theta prime t. Okay? So I'm going to bring this guy up here. So you have 2 pi fi of t equals theta prime t. And then I want to find what the original phase is. So what you can do is you can just find the integral. Okay? So you have theta t equals integral. And then fi, let me see here, 2 pi, and then, actually the 2 pi can go outside. So 2 pi, and then integral fi. And then they use different notation. They use lambda and then d lambda. The reason why is because you're integrating with respect to, so you're basically, this is the common notation that's used where you're integrating a function, and then when you're done, you substitute t in. It doesn't make sense to have a t here and then a t over there. It doesn't actually make any sense. So what people usually do is they have a dummy variable. You can use alpha or lambda or whatever. You integrate, and then when you're done, you substitute t in, and that's what happens. So when you finally integrate this, okay, when you finally integrate this, you'll get this guy over here. Okay, so this means that if you want to generate the if you want to take a look at the actual phase of your signal, it's quite easy. You just take your message, you integrate, and then this here is what's known as the frequency sensitivity. So there's two different constants. So you have the phase sensitivity, and there's also the frequency sensitivity as well. Sensitivity. Okay, and yes, so those are, so there's Kp and then there's Kf as well. So how you go from here to here is very easy. So you just go, this relationship, bring the 2 pi, to the right. And when you find the integral, you get the t here, and then there's also this relationship. We don't know what the message is, so we'll leave that. And then there's some generic constant. There's usually a plus c at the end. That's what's happening here. But the important information is that the frequency is proportional to the message. So this means that at any point in time, as the message signal changes, the frequency of your wave will change. So those are the differences between angle and frequency. So actually, if you take a look at this carefully, you can actually just use one of these methods, and then you can generate the other by either doing a derivative operation or an integral operation. So all you need is just one, but we use frequency modulation as the more often choice. Okay, so here's what I'm specifically talking about. So if you wanted to do, if you wanted to generate a frequency modulated wave from the phase, right? What you can do, okay, is if you take a look here, if I simply take the integral of my message and then this is my phase, if I use this as my phase, and so I take the integral and then I use a phase modulator, that will give you a frequency modulated wave. So that's what this relationship is talking about over here. Take the integral of your message, put it through a phase modulator, and then you'll get a frequency modulated signal. Also, what you can do is if you want to generate a phase modulated signal using a frequency modulator, again, it's quite simple. You simply take the derivative of your message, right? So in this case, this will give you the instantaneous frequency, and then this will be used as a frequency modulator to give you your phase modulated signal. So one or the other doesn't matter, but we like to take a look at FM because it's the more commonly used modulation technique. So we don't use phase modulation as much, mainly because it doesn't make much sense. We take a look at frequency modulation instead, because that actually makes more sense, especially when you're looking at it in terms of time, when you're taking a look at a frequency modulated wave over time. All right? So we're going to study FM instead of phase modulation, even though both of them are related to each other. Okay, so here's a quick example. So it might be a little odd to visualize how exactly a frequency modulated wave will look. Like amplitude modulation is very obvious. You're varying the height of the carrier. But in terms of frequency modulation, it may not look so obvious when you're trying to visualize it. So this is an example to show you what it looks like, right? So consider this to be our message signal. So this is basically a triangular wave, right? So it varies from -1 to 1, and then the period, I guess, or not the period, but the half period is 0.02. Okay, so if I wanted to find what the slope was or what the derivative is at any of these points, right, how do you find that? It's basically rise over run, right? So in this case, if you wanted to figure out what this slope is, right? It'll be 1 minus -1 divided by, and then we know the width of this is 0.02, and that's what you get here, so we get 100. Okay. Similarly, this is minus 102. So the slope in between any point in time is either plus 100, so it's constant, and then negative 100. So that's why there's a plus minus 100 here. Okay. So let's actually sketch what the actual waveforms look like. So let's assume now that the sensitivity constants are both going to be 2 pi. That way the 2 pi's and the 1/2 pi's will cancel. And then we'll assume that there's no phase offset. So there's no phase offset here, which makes things nice, right? You don't have to start at anything. And then the carrier frequency is a kilohertz. So we'll make that a little simple. Okay, so let's actually use this and then use the equations that we talked about to see what the actual phase modulated wave will look like. Okay, so remember, this is the phase modulated equation, right? Where you have your message signal that is directly related to the phase itself. And then notice that that's equal to 0. And then this guy is equal to 2 pi. Okay, so if I wanted to, so the best way to sketch this is to sketch it in terms of the instantaneous frequency. Okay, so how you sketch angle modulated waves, you always go back to the frequency. So if you wanted to figure out what, you know, the instantaneous frequency is, right? It's just so this is FOI of t, so this is 2 pi FCT, and then plus 2 pi m of t. Okay, and then sorry, not f of t. This is just your phase, right? If you wanted to find what the frequency is, you do 1/2 pi, and then you take the derivative, right? So you got 1/2 pi, and then you have 2 pi fc, right? Derivative here is t, and then you have plus 2 pi m prime of t, which is just d by dt, right? And then these 2 pi's cancel, okay? And then you're left with what we have over here. So we have fc plus. So if you wanted to draw the wave over time, this is telling you here that at any point in time, the frequency is equal to just the carrier itself, and then whatever the derivative of the message signal is at that point. Okay, so how exactly would that work? Okay, so before we do that, let's sketch what the actual derivative of the message is. So remember, in between any line segment, right, you will see that it's either a slope of 100 or minus 100. So that makes sense. So remember, the derivative of a triangular wave will be a square wave, if you remember from electronics, right? So the derivative of a triangular wave is a square wave. So this would mean that in between each change in the slope, that means the frequency is going to change as well. So remember, the carrier frequency here is 1,000 hertz, right? And then this means that so at this portion, right, what you're doing is that this becomes fc plus 100. So but the frequency between this point would simply be 1.1 kilohertz, right? And the frequency between this point, this is fc minus 100, which is not 9.9, 0.9 kilohertz. So that's what's happening. So when on the positive trend, you have 1.1 kilohertz, and the negative trend, you have 0.9 kilohertz. And then that's what the wave looks like, okay? So remember, this is your carrier. So notice that, you have your carrier, and then in between the positive points, we're adding 100 hertz. So it stays constant. Remember, this is the derivative of the message, and then you're adding that onto the frequency, and this is how you sketch it. So this is your frequency, which is originally 1 kilohertz, and then in between the positive trends, you're adding 100 hertz at every point in time, which is constant. So between here and here, you have an additional 100 hertz that's added, okay? And then between here and here, you're subtracting 100 hertz, and that's why you go down to 0.9. So it gets faster, before, and then once you transition down to minus 100, it gets slower. And then you'll see that this repeats. It fluctuates between 1.1 and 0.9, and 1.1 and 0.9. It keeps going back and forth, depending on the slope of the triangular wave. Okay, so that's how you'd sketch a phase modulated signal. So that's what it would look like, okay? All right, so let's take a look at the frequency modulated one instead. Okay, so what's happening now is instead of the phase being changed, you're taking a look at the actual frequency itself. All right, so let's see here. So remember, the instantaneous frequency is thus this. So you have Fi of t is equal to 1/2 pi, and then let's see here. So 1/2 pi, and then what's happening here is it's the let me see here. So it's 2 pi fc, and then plus kf m of t. Okay, So that's this is the actual definition in terms of the frequency modulated signal, okay? So the 2 pi's cancel, and then this here is 2 pi as well. That cancels, and what you're left with is this. So what this means is that instead of using the derivative, you're using the actual line itself. So what's going to happen is that in between the positive points, you're going to start from a frequency that's that's small, and then it'll start gradually increasing up until the maximum point. So it's going to go from 0.9, it's going to gradually increase to 1.1, and then it goes from 1.1 down to 0.9. So you can think of it as kind of like a slinky, I guess. So it goes like this every point in time. All right? So let's see here. So I'm just going to put this for now. That's fine. We don't actually need this. But what's it's saying here is that in between here and here, it's going to go from 0.9 kilohertz to 1.1 kilohertz, right? And this here varies from 1.1 kilohertz down to 0.9. Okay, so instead of it being constant in between fluctuations of the slope, it actually starts from a very small frequency to not very large, but small to big, and then big to small, small to big. So it's like you're kind of compressing a spring over time, and that's what it looks like over here. Okay, so in between here and here, this varies from 0.9 kilohertz to 1.1. Okay, so you see as the frequency starts to gradually increase, and then after this point, when the line changes, it goes from 1.1 down to 0.9. And then just for a comparison, we see that here's the phase modulated signal. So between here and here, this is a constant 1.1, and between here and here is a constant 0.9. So that's what the difference is. If you're taking a look at a triangular wave for a phase modulated signal, in between the points with the same slope, the frequency stays the same for the phase modulated signal, but for the frequency modulated signal, it gradually increases, starting from small to large, right? And then on the downslope, it goes from large to small, but then the the phase modulated signal stays at 0.9. Okay, so that's how you can sort of visualize it. So one is quite different from the other in terms of, there's one that's gradually increasing and decreasing, and then there's one that has the same frequency at each chunk in time, depending on what the slope looks like. Okay? Very simple, all right? Good. Okay, so consider this modulating waveform. So what we're going to do next is we're going to figure out what the bandwidth of a frequency modulated signal is. So remember, for amplitude modulation, the bandwidth was very easy. It's just, usually it's just twice the bandwidth of the message signal. Or if you're using single sideband modulation, then it's just the bandwidth of the message itself. But to calculate the bandwidth of an FM signal is a little unintuitive. Not unintuitive, but it's not obvious at first, and we're going to cover that very soon. Not very soon, we're going to do it right now. Okay, so let's think of this as your message signal over time. So there are positive points and the negative points. Let's say that this is a snapshot of the message signal that we want to transmit over the channel using frequency modulation. Okay, so as you can see here that there are certain points. So there are certain points where at this point here, it starts to increase, right? And then between here and here, it decreases, right? And then it starts to increase again. So this is for frequency. This is for frequency modulating signals. So you see it to the point where it starts to this is where it's increasing, and then points where you're going down, it decreases, and then it increases. So it depending on the the sign or the height of your message, the frequency of your message will change. So what we're going to do now is we're going to figure out what the spectrum of an FM signal looks like for any arbitrary modulating signal. Okay, but this is unfortunately not easy. Mainly because frequency modulation is a nonlinear operation. Okay, well, amplitude modulation is as well, but for frequency modulation, it's quite nonlinear. So unfortunately, you're going to have to approximate what the bandwidth of the bandwidth of a frequency modulated signal would be. Okay, so we're going to talk about that now. So let's start with a simple case where our message signal is just a single cosine wave. Okay, so it's a single cosine wave with a height of a sub m. So this is your message, I guess your message amplitude. Okay, this is also the largest peak. If you remember from amplitude modulation, this is the largest peak of the signal we have, and then there's also a frequency that's associated to it, right? So what we're going to do is we're going to figure out exactly how this signal will look like in terms of the spectrum, then we can also figure out what the bandwidth looks like. Okay, so if you remember what the equation was for a frequency modulated signal, it's basically this guy, right? So you want to integrate the message over time, and then there's also a sensitivity constant, which is K of F. Okay, so first what you generally do is you start off with the instantaneous frequency. Remember, frequency modulated signal, what you have is you have the actual message itself that's varying the actual frequency, and then you integrate to figure out what the general phase would be, and then you substitute this into your cos. Okay, so this is what your instantaneous frequency is over time, right? And so the frequency at any point is directly proportional to the message signal that you're trying to transmit over a channel. Okay, so this is what the general form would be. And then if we substitute m of t as am and then cosine omega mt, we're going to get this guy over here. Okay, so this kf over 2 pi factor comes over here, and then you have am cos of t, which is over there. So I'm just doing this raw substitution, which is fine. Okay. Also, what we're going to do just for notational convenience is we're going to replace this entire block with a constant which is called delta f. And this delta f constant means that it's what's known as the maximum frequency deviation. Okay, so this means that at any point in time, you will expect that the largest frequency or even the smallest frequency that you'll see in the modulation is controlled by this constant, which is called delta f. Okay, so delta f is what's known as the maximum frequency deviation. So this means that when you're frequency modulating your signal, this is the largest offset from the carrier frequency that you will expect when you're taking a look at your modulated signal. So, for example, if your carrier frequency was with your message signal, if it was 1 kilohertz and it varies between 1.1 and 0.9, as we talked about before, then the delta f would be 0.1, because that's the largest deviation that you get from the carrier that you'll ever expect in your modulated signal. Okay, so this delta f is what is known as the maximum frequency deviation. So that is the largest offset from the carrier that you'll ever expect in your modulated signal. Okay, so remember what we talked about here. So this means that the frequency deviation is directly proportional to the amplitude, which actually makes sense. So the larger the amplitude is of your message signal, the more deviation from the carrier you're going to expect, right? So if your height was, for example, 1 for your cosine wave, then it's only going to deviate in frequency by a certain amount. And then if you make your message signal very large, like 10 or even 100, then you're going to see that the frequencies will, the ranges will actually be much wider. So this actually makes sense, which means, the deviation is very directly proportional to the message amplitude of your cosine wave. Okay, so the maximum frequency deviation is independent of your message of the actual frequency of the actual message, which actually makes sense. But it's a function of the largest amplitude that you'll ever see in your message signal, which actually makes sense. Okay? So let's do a little bit of math here. So what we want to do now is we want to take a look at the phase, right? So we want to compute this, if you remember. So this is f sub I equals 1 over 2 pi and then delta prime t. Okay, so all I'm going to do is bring this 2 pi over here, and then I want to integrate. So this is 2 pi fi of t, and then this is equal to 2 pi integral, and then fi, and then lambda d lambda, I guess. And that's what's going on over here, going from 0 to t. Because you basically want to integrate and substitute t when you're done. So that's where this comes from. Okay, so we're going to substitute f of I. So from the past, we already knew this. This is basically just f of c, and then plus delta f cosine omega mt. Okay, or so that's being substituted here, and then you're just basically integrating. So this is a plus. Sorry. Okay, and then they do the substitution. So this is equal to kf am over 2 pi, and that's what's going on here. So they're just doing this because, and I'll show you in a little bit why. So you're substituting f of I, but then you're replacing all the t's with lambdas. That's what's going on here. So all the lambdas get changed, right? So all the lambdas get, from t's to lambdas. And then you're integrating with respect to lambda. So remember, the integral of cos is sine, right? So if I wanted to integrate cos of omega mt, right? This would be equal to what? It's equal to 1 over omega m and then sine. Okay, and then whatever constant you have here. So instead of t, there's lambda instead. So this is happening over here. Okay, so this is a constant that stays the same. And then what's happening here, there's a little bit of math, but it's not bad. So what they're doing here is they take the 2 pi and they multiply it through. So when they do that, these 2 pi's cancel. So then you're left with omega m, but we know that omega m is equal to 2 pi f of m, which is what is going on there. So they bring the 2 pi's in, okay? And then the 2 pi's cancel with here, so you're just left with omega m, but we know that omega m is 2 pi f, which is what's going on here, okay? So once they have this, then they finally substitute this here. That's what we already know, so this is delta f, right? They substitute that, and they put that here instead. So there's delta f divided by fm, and then sine omega m. So this is what the phase representation would be, okay? So that would be your, your theta t. Okay, so this constant here, delta f over m, is very, very important. This is what is known as, you can think of it as a modulation index. So remember, you had the amplitude modulation, there was a modulation index. You could think of this as the modulation index for FM. Okay, so that basically just tells you, I guess, how much of deviation or how much deviation you'll expect from the carrier in your frequency modulated signal. So this is a measure that's used to, I can not only assess the quality, but also determine how much deviation you're going to get with respect to the carrier. Okay, so we can finally express a frequency modulated signal as the following. So we know that this is what we wanted to solve, because this is the general form for your frequency modulating signal. So we had to solve for theta t first, which is over here. We figured that out from previous slides. So this is the previous slide. Okay, that's what we have here. And then we're going to change delta f divided by fm with beta, and that's what we have here. Okay, and then where you go from here to here is very simple. Remember, when you have an addition of 2 values inside a cosine, it's simply equal to cos A, cos B, minus sine A, sine B. And that's where that comes in. Okay, so you can think of this guy as your A, and you can think of this guy as your B, and the result follows. Okay, so you have cos A, cos B, so this would be A, this is B, and then minus sine A, and then sine B. Okay, so that's where that follows. And remember, this is for a single tone signal for your message. So that means that the message signal is just a cosine wave, right? And the height doesn't change over time. Okay, we're going to do a little bit some more of trigonometric stuff here. So this is what we had originally. So this is what we had, not originally, but this is after we do all the substitutions. So once you break up the cosine into a product of cos, and sine, and then we're going to take a look at varying cases. So the first case is if you have what's known as a narrowband FM signal. So what the narrowband FM signal means is that the bandwidth of the signal is actually very small. So remember, if delta B is equal to, not delta B, if beta is equal to delta F over FM, right? If beta is small, therefore delta F is small. So that means that the amplitude, not the amplitude, but the frequency deviations are small. So that means that the message signal may be tiny, or the sensitivity constant may be tiny as well, but it doesn't deviate much from the carrier. The actual modulated frequencies don't deviate much from the carrier. Okay, so in narrowband FM, usually if it's small, typically we consider a narrowband FM to be when the modulation index is less than 0.3. If it's something very small, if you take the cosine of a very small number, it's approximately equal to 1, which makes sense, right? Because your cosine wave is going to look like this, right? So if your value is very small, then it's going to approximately equal 1, okay? Also, what we talked about before, I don't know if you remember, but if you want to take the sine of a very small number, it's actually linear, right? So if your sine wave looks like this, right? So sine wave looks like this, I guess, right? Within a very small range, right? You can consider sine of x to be approximately linear, and that's the relationship that they're going with here. So if the argument is very small, then you might as well approximate it with just the argument itself. So it's approximately linear if the argument is very small. So if you do this instead, if you assume that the modulation index is very small, then what we can do is that we can change this, because it's approximately equal to 1, right? So that's what's happening here. Okay, and then we can change this so that it's just beta sine omega mt, because it's approximately linear, and that's what's going on over here. Okay, so if you have a case of narrowband, if the modulation index is pretty small, or if there's not much deviation away from the carrier, then you can approximate the frequency modulated signal as just a sum of 2 cosines, or 1 cos and a product of 2 sines. Okay, so that's what happens when it's very narrowband or if it's very small. Okay, so there's actually, if you actually take a look at the signal carefully, you can see that there are some similarities with regards to amplitude modulated signals. Okay, and I'm going to show you why that is. So how exactly does, narrowband FM, or the case where the frequency deviations are not that large from the actual carrier, how is that actually related to amplitude modulation or large carrier modulation? Okay, so remember that this is the case where the message signal is just a cosine itself. This is not, we're going to talk about general message signals later, but just for now, just consider the case where the message signal is just a cosine. Okay? How does this compare to amplitude modulation when you're taking a look at a single tone? All right, so if you remember what amplitude modulation was, it was basically AC plus M of t, and then cosine omega ct, right? So this guy here would be your message signal. That's what we had before. So you're just substituting that in. Okay? And then what's happening now is we're going to do a little bit of math. We're going to factor out an AC term. So then when you factor out an AC term, there's a 1 here, which makes sense. And then when you factor out an AC term, you have to divide by the constant. So that makes sense. So if you actually were to expand these out, you'll get the top. Okay? So this is what the factor version looks like. Also, if you remember, the modulation index was equal to the largest value of your message signal divided by the carrier. And the largest value, if you remember, is just simply the amplitude of the message itself, right? Because this is just a single tone, or it's just a cosine wave of A of M, and then there's only one frequency at that for that particular cosine. And then if you consider this, if you do this substitution, then you'll just replace this with mu, which is that modulation index from here. And then what you can do is you can just expand out, all right? So you can expand this out here, you can also expand this out, and then you get this expression in the end. So if you actually compare this with your, with the frequency modulated signal for the narrowband case, you'll see that there are some similarities. Okay, let me show you that right now. Okay, so this is what this is. So this here is your amplitude modulated signal. This is from the previous slide, where this is the narrowband modulated signal, narrowband frequency modulated signal, where the modulation index is less than 0.3. That's the threshold that is used to determine whether or not something is narrowband approximately. So you can see that there's a carrier, and then you're adding on top a modulated periodic signal or cosine. So one of them has a product of 2 coses, and the other one has a product of 2 sines. And you'll see that one of them has a plus, and then one of them has a minus. And then you also see that there are the modulation indices for each thing by itself. And then instead of coses, you have sines. So they're actually quite similar. But what is generated is actually quite different in terms of what is seen in the output. Okay, so here are some observations. So single tone amplitude modulation and narrowband frequency modulation are actually quite similar, yet they're very distinct modulation schemes. Remember, one adjusts the height of the carrier, the other one adjusts the frequency of the carrier to transmit the signal over the channel. Okay, so as I talked about before, in terms of similarity, we know that the AM modulation index, this is simply MP over AC, assuming symmetric. Okay, and then here, this is the modulation index for FM signals, as I talked about before. So it's just the frequency deviation. In this case, this is KFAM over 2 pi. And remember, this is only for single tone. So only for single tone. This is only for single tone modulation. So that's that's if you want to do it like that, right? So that's only for single tone. So as I talked about, applicable for only single tone. So these constants talk about the maximum deviation or the quality of your signal with respect to their respective domains, and that's about it from there. Oopsie. Okay, so this is a way to, this is a narrowband frequency modulated signal. This is for a single tone. Okay. So this is a block diagram of how you actually generate narrowband frequency modulated signals if the message is not a single tone. You'll see why this block diagram is the way it is. I just want to give you a quick overview or a quick, teaser of how exactly you would generate a narrowband frequency modulated signal using any general message. So I'll actually derive how this is done, but I just wanted to give you an overview of how exactly this works. So what you do first is you have your message signal. This could be your cosine, right? You integrate it first, and then what you do after is you multiply this by AC sine of omega t. So this portion here is this part, Okay, so that's what's happening here. And then you're going to subtract this with your carrier, which is this part over here, and then you generate your output. So why exactly this is, remember we just used the cosine, but why exactly, you're doing, in terms of the general message, I'll talk about that later. Okay, how exactly, this is derived. But I just wanted to give you a quick, glimpse of how exactly you would generate a frequency modulated signal, but assuming that it's narrowband, or if the modulation index is very small. You first integrate the signal, multiply by AC sine, and then you subtract with AC cos, and then that will give you the output. Okay, but I just want to give you a little bit of a teaser, just in case. Okay, I'll go do a couple more slides, we'll take a break, all right? So this is what the Fourier transform, or the spectrum of a narrowband frequency modulated signal would look like for a single tone signal only. Okay, so we've already derived this relationship. That was already done. So what you can do is, we can actually split this up using trigonometric identities, right? So if you remember, sine of A and sine of B is equal to a half cos of A minus B, and then minus a half cos of A plus B. Okay, so this stuff will be given to you on your midterm. So you're not expected to memorize this. These relationships will be given to you on the midterm, so you don't have to memorize. All right, so when you use this formula here, this is A, and then this is B, you get the following, as you see over there. Okay, so you have your carrier, right, as by itself, and then you have two additional cosines that are scaled by AC beta over 2. So that factor of half comes into play over here. Okay, now if you wanted to take the Fourier transform, okay, if you remember the Fourier transform for a cosine, omega naught t. If you take the Fourier transform this in terms of f, it's a half delta f minus f0 plus a half delta f plus f0. Okay, so you have two impulses, okay, defined at f of c, which are going to be scaled by a half. That's what the AC of 2 is for. Okay, so that is over here. Okay, and then you have 4 more impulses, one centered at omega c minus omega m, which is over here, and then notice that your amplitude is AC beta over 2, but then you have to divide by 2 again, so it's AC beta over 4, so that's why it's scaled by half. And then you also have minus becomes a plus for the omega c plus omega m, and that's what you have over here. Remember, there's 2 copies, one on the right side and one on the left side. So if you actually find the Fourier transform of this relationship, that's what you get as a result. Okay, so pretty standard. Okay, and then also for the narrowband case, also take a look that the bandwidth that you need is just simply twice the message. Okay, so remember, so the difference between here and here is simply f of m, and then the difference between here and here is also f of m as well. So if you take the difference between here and here, you get twice the bandwidth of your message. So that would be the bandwidth that is occupied in the channel if you wanted to transmit a single tone, which is a cosine wave, using frequency modulation over the channel that you want. So if you have a narrow band single tone frequency modulated signal, then the bandwidth of that signal is simply twice the actual frequency of that cosine wave. Okay? It's also same as amplitude modulation too, so I should probably point that out as well. Okay, so I'll tell you what, guys, we'll take a break now and then come back in about 10 minutes and I'll continue on from here. Okay?